Hi all. Can you see the slides?
Yes, sir.
Thank you. So let me wait for 3 to 4 minutes. Then I will start. Okay, guys. Let's start. I'm Anand Bandyopadhyay. I'm doing PhD in CNS lab under Professor Srinivasan Chakravarti, and I am going to give you a short tutorial on basic dynamical system and physical analysis. So I think you got a little bit of idea about the dynamical system in the morning sessions. So this session I'll do a little bit recap of those ideas and then how we can implement those ideas in our applications. And if you feel a little bit overwhelming, you can ask me any times, and it will be very good if it is a interactive system, and we can try to make you familiar with this kind of dynamical and linear and non-linear dynamical systems. And I also gave you uh, one code, one notebook that also you can use. And later we'll use two systems. One is XPUT, this one software for dynamical systems, and also we can use one MATLAB app that I built earlier. So just let's start with this basic theory of dynamical system, and then we'll do those applications. So uh, the topic will be, first we'll try to understand what is 1D systems and why do we need this dynamical system analysis. Then we'll go to understand linear 2D systems, then nonlinear 2D systems, and we'll understand while linearization Jacobian is needed. Then we'll do a little bit of analysis on XPPUT and the pendulum system with and without dampings. Then I will give you a little bit introduction on the bifurcations, limit cycles. Then I will talk about oscillators and what is hop oscillators and different kind of couplings. So in our lab, we mostly works on this kind of hop oscillators. So before going to hop oscillator, I think it's needed to understand a dynamic system from a very like 1D systems first, and then we can go on and understand the oscillator system. So I think we know how to solve a differential equation, right? So let's take a very easy, simple differential equation, which is dx by dt is equal to sin x, right? So there are lots of methods we can use it, like the methods we used in our 11th and 12th standard, like take the sin x under dx and do the integration. So it will be like dx by sin x, integrate it, and also integrate the dt. And there are also various methods like Newton-Raphson's method, Euler's method to solve these differential equations. Yes. Hi. Do you want to ask anything? Hello. If you want to ask anything, you can just switch on your mic and ask me, or type in the group chat in the message.
Hello, sir.
Yeah, I can hear you.
Yeah, you have just talking
Uh,
about limit circle.
yeah.
Sir, please explore properly, okay?
Yeah. Limit cycle and all. I will explore those things, those
Okay.
concepts. So you see, so first time to talk about a little bit 1D system, then I'll go on to talk about the limit cycles. So for solving this kind of systems like dx by dt is equal to sin x, we can plot this sin x in an x dot versus x graph. And when you plot this, we see there are some positions when the x dot is greater than 0 and some positions x dot is less than 0. So when x dot is greater than 0, we can give an arrow rightwards. So it means that if we see these systems on a line, like on a x plane, so this x vector is moving right order, like a positive or negative directions. We can say that right or left. So when it is greater than 0, we can think that it is the solution is growing solutions. So we just point the arrow to rightwards. So that's written here. So the arrow points to the right when x dot is greater than 0, and when it is negative, we can think that the solutions can go to negative directions. So you can give a arrow to the leftward. So it's a leftward arrow. So by looking at this, we can kind of understand the what the solution looks like. So at the pi, you can see there is a two converging solutions, and at 2 pi there is a two divergent solutions. So even if you look at this, how the solution grows from pi by 4 to pi, so there is certain increase and there's a downfall and there is a steady state. So by this way, you can understand how the solutions will be for a 1D system. Even if you plot these 1D systems and do the quantitative analysis, it is a similar. So by this qualitative, looking at the qualitative analysis, we can get the understand how the solution of the system will be. So this is a very basic 1D systems. Now look for the 2D systems. Let's say we can um, design a 2D system by this x dot is equal to ax plus by and y dot is equal to 6 plus dy. And this a, b, c, d are parameters. Let's say these are the positive numbers. And we can just say x dot is equal to a bold-faced ax. So the let's say this large x front is like x and y, and the A is a matrix of A, B, C, D. And we can kind of understand how the solution will be. So people thought that to solution of the this kind of linear systems will be like eigen solutions or the general solution of the systems. So we can write it as e to the power lambda t and v. So then if we do the differentiate of the e to the power lambda t and v, we'll get a very simpler form, like av is equal to lambda v. So it's perfectly look like a eigenvector, like characteristic equations of the eigenvectors. With the v is the eigenvector of a, and with the corresponding eigenvalue lambda. It's nothing but we are scaling this v vector when we're multiplying the a. So if please follow these ideas, then you can write the characteristic equation like determinant of a minus lambda I. As you know from our high school physics that we can find these again solutions from this type of characteristics equations. And let's say there is a 2D system, 2 cross 2 matrix A, B, C, D. We can calculate this lambdas or eigenvalues, and after this we can get a characteristic equation that looks like lambda square minus tau lambda plus del is equal to 0. So we can calculate those traces like a plus d and the determinant of a ad minus bc, and we can also calculate this by multiplying the determinant by multiplying lambda 1 and lambda 2, and trace by simply summed of these two eigenvalues lambda 1 plus lambda 2. So as I talked about earlier, the general solution of the xt will look like this, that there will be some large font xt will be c1 e to the power lambda 1 t v1 plus c2 e to the power lambda 2 t v2. So if it's the general solution will be like this. So at initial conditions, when t is equal to 0, it will be nothing but the linear combination of those this eigenvectors. So it will be like c1 v1 plus c2 v2. I hope it is okay to everyone, right? So you need to understand each steps as you go forward. If you need any like clarification, you can ask any questions. Just switch on the mic and ask me.
Hello.
Hi.
Hi. This is a very simple question. Actually, I don't understand any maths at all.
Okay.
So I just wanted to ask,
Uh,
why we are doing all this thing, like this,
okay.
the purpose of what we are leading to after doing, matlab, if you get my point, like what is the
Yeah.
basic idea of this thing?
Okay. Got it. Got it. Got it. Got it. So the basic understanding of this that when we solve a differential equation, right, we can solve the differential equation 2-3 ways. One way of the solving differential equation by simply numerical analysis by these Euler's methods. We just solve the differential equation by each time points. And but there is some differential equation which is not easy to solve. So and it is time taking. So there is a better way to solve this differential equation by simply looking at the doing this qualitative kind of analysis. What the possible solution will be. So there will be two cases. So we can design different kind of systems to understand the natural phenomena. Like let's say how the water flow in a pipe. So we know there are lots of differential equations to understand those. So to understand those kind of concepts, it's needed to build different kind of differential equations and to solve those different kind of differential equations. So it's a two-way. It helps to design differential equation and solve the differential equations. So by simply solving numerical solvers, like we have this OD45, OD15 in MATLABs and in Pythons also, this inbuilt differential solvers. Without using those differential solvers, how we can understand differential equations? How we can understand the differential equations and solution of it by simply doing this qualitative analysis.
Okay, yeah, yes.
Have you got my point?
Yes,
think
yes, I got it.
I think it will be more clear when you go forward through the slides that how we
Okay.
can understand this kind of like this kind of analysis.
Mm-hmm. Okay, yes.
Yeah. So even for solving this kind of differential equations like x dot is equal to x plus by, y dot is equal to cx plus dy. So this kind of differential equation you can see in the metabolites. If you solve this, I think first order differential equations, how the different kind of enzyme kinetics works, right? So it's very easier to understand how the enzyme kinetics by this kind of qualitative analysis. Like we are trying to predict the solutions by this kind of analysis, not just numerically solves each time points. I hope
Okay.
I clarified the
Yes,
point.
yes, you have.
Thank you. So here I give the idea that how we can solve this differential equation, like 2D linear differential equations. So can you try to do this, solve this differential equation by the techniques that I just mentioned? It's very easy. Dx by dt is equal to x plus y, and dy by dt is equal to 4x minus 2y. Can you try to solve it? And I can wait for 1 or 2 minutes, and hopefully you'll get answer. So if you have any questions, you can switch on the mic and ask me. So look at the differential equations, the coefficient of the differential equations, like what is added multiplied with x and y each time. See here, it is a b c d. So here ab will be 1, and c and d will be 4 and minus 2. Has anyone tried this? Let me go forward the solutions of it. It's very simple. We can write these equations, x dot y dot, by this matrix ABCD. So as I told you that a and b will be 1 and 1, and c and d will be 4 and minus 2. So we can build up this characteristics equations, which will be like lambda square plus lambda minus 6, and the lambda 1 will be 2 and lambda 2 will be minus 3. So if we solve this, we will get this kind of solution of the differential equations. So this C1 and C2 are constant, and you can get C1 C2 from these initial conditions. So it was not very difficult to solve this. I hope you guys understand this, because it's very necessary to understand the linear 2D system first. Do you guys have any questions? Then ask me. Let me go forward to different kind of terms and definitions that are there for the differential equation, like nonlinear dynamics and linear dynamics. Here I'm telling you the definitions, and when we go forward, we'll understand those concepts and definitions further. So one of the terms that I'll use further in the slides, that is fixed point. So what is fixed point? Fixed point in the dynamic system is that when the state variable doesn't change at over time, or x dot is equal to 0. You see in the my first slide, in x dot is equal to sine x, at pi, 2 pi, the value of the sin x is 0, right? Sin pi, sin 2 pi. So these are the fixed point. Then there is another concept that is NURC lines. So NURC lines are the lines where x dot is equal to 0 and y dot is equal to 0. So what does it mean? Like if you plot in xy plane, x plus y is equal to 0 and 4x minus 2y is equal to 0, then you'll get the x NURC lines and y NURC lines. There is another concept called periodic orbits. So periodic orbit is like the when you get a periodic solutions. In xy plane, it will be like round and round, going on forever. So this is called periodic orbit. Then I'll use a term called phase plane. What is phase plane? When you show how the differential equation evolves over time in a xy plane. So in the first slide, I showed this x dot versus x graph, right? And the vector fields or velocity vector of x in a line. So we call it a flow on line. If you plot this on xy plane, it will be all over the places, like all over the xy plane. And you'll see just a minute from now. And the bifurcation is like if we change some parameters of the differential equation, how we can get different kind of solutions, like fixed point, periodic orbits, and all. So let's look at the system that we just solved. We get two eigenvalues. One is 2 and one is -3. So now go back to our original concept, that what is the general solution of the xt? General solution of the xt will be like c1 e to the power lambda 1 t v1 and plus c2 e to the power lambda 2 t v2. Now if you put lambda 1 2 and lambda 2 -3, so one solution will be growing forward, like exponentially growing, and another solution will be exponentially decaying. So it's nothing but we plotted this solution in a xy plane, and you can see from the plot that one is exponentially growing from the fixed point and another is exponentially decaying. So this kind of fixed point, we can say that we gave a term that's called saddle points. And how the solution looks like when we go a little bit away from the origin of the fixed point, that's also has been given here. So let's look at the other kind of solution system. So as you know that we have the general solutions, xt is equal to c1 e to the power lambda 1 t v1 and plus c to the power lambda 2 t v2. So this lambda 1 and lambda 2 will give, let's say they are the complex number, like alpha plus I omega. If they are alpha plus I omega and this alpha is a real values and omega is is an imaginary number, then you can see this solution looks like a spiral. If alpha less than 0, it will be decaying, and if alpha is greater than 0, it will be growing amplitude. And another thing is called center. What does it mean by center? When you will get a closed orbit. I told you, right? So sometimes you get a closed orbit, and this closed orbit are just kind of periodic solutions. So you just put I omega. So there is no, let's say there is no real numbers. So only I omega will be there. So if it will be like c1 e to the power I omega t v1 plus c2 e to the power I omega t v2. So it will give only sine and cos, sinusoidal and equations. So it will be like periodic ones. So we can see this kind of system in a harmonic oscillators. Let's say pendulum or spring mass system. So there are lots of classifications of the fixed point, and you just calculate this tau and del. What is tau and del? Tau and del we calculated earlier. You see here we calculate the tau and del, which is the trace of matrix and determinant of matrix. We can calculate by simply a plus d or from the eigenvalues also. Tau will be like summation of the eigenvalues, lambda 1 plus lambda 2. They will be like multiplication of the eigenvalues, I think lambda 1 into lambda 2. So we can, from this, when you find out the tau and del, you can plot this tau and del and try to find out where the tau and del, where the tau and del position is. If the del is 0, and then you can call it at the center. And we can calculate tau square minus 4 del. If it's greater than 0, then it will be like unstable node. If it is less than 0, it will be like unstable spirals. So by this way, we can understand that how the fixed point will be. So understanding the fixed point, we can get to understand how the solutions will be. Like if we find out that it is center, then we know that it is a periodic solutions. If we know that if it's spirals, then we can understand it is either decaying or growing amplitude solutions. Let's say damping of the pendulum system, right? So from this understanding, we'll go forward to understand what is the nonlinear system and nonlinear 2D system. We understand the 2D system, linear 2D system, and to understand nonlinear 2D system, we actually transform the nonlinear system to a linear system by linearize it. And what is meant by linearize? So we do a Taylor series expansion, and if we take a small disturbance, actually we'll found out if we do a small disturbance of the systems, and it actually like evolves a Jacobian series. So what is Jacobian? Jacobian is nothing but taking the differential equation of the each functions by its xy terms. So Jacobian will be like del f by del x, del f by del y. In the first row, in the second row, it will be del g by del x and del g by del y. If your function will be like f and g. So the pipeline will be simple, same differential equations, but before finding ABCD, we'll do a Jacobian around the fixed point, and then we'll go for the eigen solutions. I think it will be much clearer if we see this pendulum. So pendulum, I think you all studied pendulum in 12th standard, 11, 12th standard. And I think it's the first nonlinear systems that we encountered in our schools. So in classic pendulum is given by this second order differential equations. If we just remove those G and L terms, which is the length of the pendulum and the gravity, we'll get a very simple dimensionless system. That's the double differential equation of the theta plus sine theta is equal to 0. So let's say this theta is like how the pendulum is some kind of theta angle with the vertical columns, and if we keep the pendulum with some theta angle and release it, we know it will give some kind of oscillations, right, from our physics understanding. Let's see from the dynamical system we can get the similar kind of understanding or not. So that's the objective of these topics. So this from the second order differential equation we can form these two first order differential equations. One is theta dot is equal to v, and is the v dot is equal to minus sine theta, right? So as I told you, for this nonlinear systems, as you know that this is not a linear system, this sine theta is not a linear terms, so we can do the Jacobian. And when we do the Jacobians, what we'll do, we'll take the differential equations, the differentiations based on these functions like v and minus sine theta. If you do that, like what will be, it will be like del theta dot by del theta dot by del v dot by del theta, and del v dot by del v. And around the fixed point like 0, 0 and 5, 0. So when we got the two differential equations, first thing we need to understand what the fixed points are. So two fixed points are there. One is 0, 0. This is the obvious solutions for this v is equal to 0 and sine theta is equal to 0. And for sine theta is equal to 0, there are lots of solutions, right? Like we can say pi solutions, n pi solutions, pi to pi, all the solutions for the sine theta is equal to 0. So let's focus on these two solutions. One is 0, 0 and another is the pi 0. So if we get the solution at 0, 0, the A matrix after Jacobian will look like 0, 1 and minus 1, 0. If you do the eigen solutions of this, we'll see that it looks like a closed orbit or center. So as I told you, this closed orbit or center looks like a periodic solutions. From here we discuss this, that why this closed orbit looks like a periodic solutions. Because if you do the if you calculate these eigen values lambda 1 and lambda 2, it will produce a imaginary number. So you just simply put lambda here, right? You'll get a lambda square plus 1 is equal to 0 at 0 solutions, and lambda square plus 1 is equal to 0. All the solutions of the lambda will be in imaginary term. So that's why it will give you a periodic solutions or the closed orbits, or we can call it a center. At pi 0, we'll get a saddle points. That is also we discussed earlier. So I think one will be plus 1 and one will be minus 1. These two eigenvalue solution you'll get. So this is the whole, if you plot this system theta and v for all the solutions, we'll get this kind of diagrams. And this kind of diagrams is actually called a phase plane. I think I earlier talked about the phase plane here. So what is phase plane? Phase plane is a plane, it's kind of plot in a 2D system. And when we plot all these solutions of it, its trajectories, its fixed points, mark lines, and then you try to understand how the trajectories or the solutions evolves over time. So that is it. So let's try to look at and interpret the system. So let's say we are at center, or we are at 0 solutions. What is saying that we'll get a periodic solutions, right? So if we leave our pendulum from very small angles, let's say our pendulum is angle of theta, and theta is very small, so naturally the initial velocity v will be very small. When it's very small, what will happen? It will do oscillations. The pendulum will be moved like back and forth, right? So dynamic system people call it librescence, but we don't need to remember those terms. We can call it simple oscillations or back and forth oscillations, and it doesn't swings or sorry, it swings, but it doesn't flip over. Like it gives us oscillations back and forth. And if the theta is, let's say we increase the velocity and to keep the theta in a vertical position at pi. So when the, let's say this theta is pi, means that this pendulum will be will be like inverted positions. At theta is pi means it's a inverted position, right? When you leave the pendulum at that position, it will give a pure rotation. It will be much larger velocity, and we'll see a full rotation or continuous spinning of the pendulum. So this kind of understanding we can get from this qualitative analysis of these differential equations by simply getting the eigen solutions, plotting these phase diagrams. We can interpret the systems, like how the system behaves, different kind of initial conditions. So if the initial condition is between 0 to pi, then it will be like oscillations, back and forth swings. If it's more than pi, or it's then we'll see a simple rotations, or at pi you will see a simple rotations, right? So let's say if it's a damped pendulum. So in damped pendulum there's another term, that is mu dx by dt. So if it's a damped pendulum, if you studied damped pendulum earlier, you see that in a damped pendulum we will not see this kind of oscillations behavior. So it will be a decaying oscillations. So we leave the pendulum for some time, and after some time it will be at a 0 positions, right? So even if we plot this damped pendulum, then you will see this kind of system at the 0 solutions. We can see a spirals, right? And the decaying spiral. So it starts from some theta, and eventually it goes down and decaying, and it's stabilized at 0. So I'll show you these two systems in a XPPOT softwares, or I also gave you one um, Python notebooks, and when you can plot those systems and see how it looks like. And if you want to know lots about the XPPOT, they have a good documentations, and this is the way you can write the XPPOT equations. They have a definite .ode files where you can like just write down those differential equations, mention the parameters, and then at the end you have to write a done. I mean, this is the end of the differential equations. Then you can plot it. I'll show you just mm, after I finish the theories of it. So this kind of systems we can say oscillator because it's giving the oscillating behavior, right? There are very definite kind of system that people have studied and built up in from 1990s to 2000s. This kind of systems called so we used a different kind of system that's called a Hopf oscillator. This Hopf oscillator, it's driven by the term driven by the phenomenon called Hopf bifurcation. So I used bifurcation term earlier. If you see here, I gave the term bifurcation. So what I said earlier, that bifurcation is a system when we change the parameters or vary the parameters, we can see different kind of solutions like fixed points, periodic orbits, etc. Right. So here also we can see that when we change the parameters, so there is a two differential equation. One is r dot is equal to mu r minus r cube, and another is theta dot is equal to omega plus br square, where mu is the bifurcation parameter and omega is the intrinsic frequency of the oscillators. So when mu is less than 0, we'll see a spiral behavior, decaying spiral. And when mu is greater than 0, we'll get a limit cycle. So limit cycle is nothing but it gives a periodic solutions. So there's a little bit difference between the limit cycle and the closed orbit. You see the closed orbit are surrounded by defined closed orbits. Like there's a growing closed orbit 1, 2, 3, and in limit cycle is surrounded by mainly the other trajectories, not by the closed orbit. So we can see this kind of system by simply just um, see the video of it. So here I plotted mu from -1 to 2. So just let me once again run this. You see, it started from spiral, and then it's becoming looks like a periodic solutions or kind of a closed orbit. But this closed orbit we gave a different name, that is a limit cycle. So this is a simple Hopf oscillator, right? Let's say we try to understand how we can couple two different Hopf oscillators. So Hopf oscillator. So here I wrote the Hopf oscillators in XY form. Also, you can write the Hopf oscillators in the complex term. So if you write the Hopf oscillator in a XY form and couple these two Hopf oscillator with some kind of real values number, let's say k. So then we call it a linear coupling. And if we couple them by some kind of complex values, then we call it a complex coupling, like a to the power I theta. So see, in for Z1 solution, it is like Z1 dot is equal to Z1 in bracket mu plus I omega minus mod of Z square and plus a to the power I theta into Z2. So that's how we can include the Z2 term in the Z1 term. So this is called a complex coupling of the Hopf oscillators. Remember, the mu is the bifurcation parameter here. So if you change the mu, the system will varies. So if mu is the 1 or greater than 1, we'll get a limit cycle. If mu is less than 1, we'll give a damping oscillations. That's actually showed by this spiral behavior. So this kind of systems were there, and but we go forward and build a little bit different kind of coupling hypothesis. We call the power coupling. So let me just call what is the difference between the complex coupling and power coupling. And in later talks, I think Rohan will go forward and talks lots more about this kind of coupling behaviors and how we can use those kind of oscillators in a machine learning algorithms. So let's say there's two oscillators. It's given by Z1 and Z2, and it's coupled by a to the power I theta and a to the power minus I theta. So these are the Hermitian matrix. By this we can set this kind of systems. And but what is the problem if we couple these two oscillators by the simple complex coupling? So we see that if the frequency of the oscillators, so these oscillators have a natural frequency. By this frequency, this hop oscillator oscillates each time. And if this omega 1 and omega 2 are very similar, we'll get a steady state phase difference. Let's run this video. You see here this omega and omega 2 is very similar to each other. So you'll get a steady state solution. In case the omega and omega 2 are not similar, then what will happen? If omega 2 and omega 1 is not similar, then the solutions never become a steady state. How far we try. So we try to find out and come up with a different kind of system that's called the power coupling, where with the Z1 term we introduced a power of the frequencies like omega 2 by omega 1. See in the box, you can see that in the Z1 term we'll use W21 into Z1 to the power omega 2 and omega 1. So how the Z1 will be come to Z2, Z1 or Z2 will come to the Z2 term by some power of omega 2 by omega 1. And that's and if we plot this in a normalized phase difference like phi 1 by omega 1 minus phi 2 by omega 2 minus theta by omega and omega 2, we'll see that the solutions ultimately will come down to a steady state phase difference. Now you will ask me that why we are doing this kind of complex systems, like how you were doing this power coupling, and why do you need normalized phase difference? The simple answer of this is that how the brain works. We know that in the brain we have a different segments, right? And each of the segments have a different frequency. Some lower frequency, some higher frequency, and but still with these different frequencies, the brain interacts. These different parts of the brain interacts with each other. So how we can build a system by which the brain interacts with each other? So we come up with the idea that we can use simple oscillator. So there are lots of systems like computational neuroscience. They have a Hodgkin-Huxley model and lots of very detailed neural models to understand brains. But we are saying that we can simply understand brain by simple oscillator. So this each oscillator kind of mimic one brain region, and this oscillator will have different intrinsic frequencies. So they will oscillate with these intrinsic frequencies, and how they couple with each other by these power couplings. So they will talk with each other so that they have a normalized phase difference. So I will explain this power couplings and the complex coupling with this MATLAB app, and I think now we'll do the tutorials. And all of my theories that I described is from the books Nonlinear Dynamics and Chaos by Steven Strogatz. If anyone is interested in understanding nonlinear dynamics, linear dynamics, I ask them to actually read this book. It is very good, very easy to understand. Even he has his own course in YouTube, in free of cost, from Cornell University. You can go to the playlist, and it's a very good, very lucid understanding of the nonlinear dynamics. And if someone wants a very crisp understanding, so these videos are a little bit longer, more than 1 hour for each video. You can go to the Dynamic System by Jason Bromberger. Here's also some YouTube videos that's 20 or 30 minutes long. From there also you can understand this kind of dynamical systems. So let's go and try to understand the little bit more about the different this dynamical system from the notebook and the XPQT software. I hope you can run the XPQT software if you have downloaded in your desktop. In the meantime, I will also set up the XPQT software in my system. Hi guys, can you see the screen?
Yes, sir.
Okay, good. So let's open this XPPOT software here. I think those who have downloaded by in Windows systems, you'll get this shortcut, and if you run it, you'll give this kind of GUI system, and you can go to the OD, and in the OD you can just simply write pnd.ode. So it's the actually they have the already they have a file for understanding the pendulum oscillations, and what is the equation for it? If you want to understand, you just simply click the equations. So you see this the damping equation for the like dynamical system equation for the damping pendulum, and so just close it, and and you see those parameters and all m mu this g and l, all the parameters are there, and how the phase plane will be if you have to guess. So already I told you that the phase plane of the pendulum will be a spirals, right? Decaying spiral. We just plot it. You just click go and you'll plot the spiral plot. And what about the vector field in the xy plane? We can just go down and click the directed field and click it. And if it wants us to give some grid number, so let's keep it at 16 only. So then we'll get the how the solution will be, the trajectories of the solutions in all xy planes, right? So here the theta and v that I described earlier is given by x and xp, right? Now if you want to erase those systems, so you can click erase, so it will erase it. And if you want to see that what kind of parameters you are taking, we'll get these parameters like M is 10, mu is 2, G is 9.8, L is 1. And let's say if now mu is 2, if we just click mu is 0 and simply go, we'll see you'll get a periodic orbits. So periodic orbits is for the undamped pendulums systems phenomena. So by this way, we can actually calculate the understand the damped and undamped pendulum by these XPPT systems. Let's close it. And there are lots of different kind of lots of ODs are there in the XPPT software. You can try to understand and see what's giving in each topic. So let's say we want to understand what is X versus T. So let's say we want to take X versus T. See, it's a periodic solutions, isn't it? Even we can change the axes. We click the axis, go to 2D. Let's say we want something Y mini at 0. Click OK. It skips 0 to 2. So lots of different things we can do with this XPPOT softwares. It will be very good if you try to understand the dynamic systems and explore the XPPOT softwares to know that the kind of trajectories that you are estimating it's true or not. Now let's close these systems and go to this Python notebook. Let me run this first block. This first block is the blocks for the undamped pendulum. Nothing, you just write a differential equation for this theta and v, like v and is minus sine theta. Then you solve it and solve for the different trajectories. Initialize different kind of solution, solution range, and when you solve it, you will get a very distinct behavior. So you see at theta 0 to pi, it will be like closed orbit, a pendulum kind of the periodic oscillations behavior, as I told you earlier. So it is like oscillations. And if we go beyond the minus 3.14, this beyond pi and above it, you'll see a distinct rotations. So if you keep the pendulum in a inverted positions and release it, it will have a full swing, full rotation of it, right? So this black lines tells you that how the two systems different. One is simple oscillations with smaller theta, smaller v, and rotation with the higher theta and higher v. And let's say we click on the second blocks. We'll get a, if mu is 0, you'll get a simple undamped pendulums. We'll get the closed orbit like periodic solutions, and also the rotation above top of it. But if we introduce some kind of damping, then we'll get a spiral. It means the solutions will come here, 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 and it will die. That you can see in a damping pendulum, right? So this will tell you how the two systems are different, the without damped and the damped. So anyone has any questions about it? Please switch on your mic and ask me. If you understand the dynamical system, the phase plane, and how we can do it. You guys also try in either XPPT software or try in a notebook also.
Yeah, hello.
Yeah, hi, I can
Yes,
hear you.
sir. Yeah, hello, sir. I just tried opening the XPP but it does not seem to open for some reason. I don't know why.
So the problem is that it's a very older software. So sometimes in some system doesn't work. Do you have a Mac
Yeah, no, it's Windows.
in Windows? So Windows it works in Windows. So I have a Mac. So I have a problem in this Apple Silicons. So other
Okay.
than that, I tried it with both Linux and Windows. With both cases it works well.
Ah,
I
okay.
think have you remove your system to the C drive, like
Yeah. I copied that directly to the root directory of C. Right.
C drive, right?
Yeah.
And have you copied here also?
I
If you
mean,
could search.
I sent you a message by afternoon, right? It opened, like it was me who sent that. It opened
Oh,
that time, but now it's not opening for some reason. I don't know why.
maybe have you downloaded this Asming also? This viewers and all.
Ah, yeah.
Oh, then I have no idea why it's not opening. But sometimes it happens because
It just says failed to open X display.
okay. Then I think okay, got it. Then I think you have to re-download this Asming. So they have a latest versions also. Download the latest versions.
Okay. Maybe
Then
I'll
I hope
just.
it will work for you.
Okay, sir. I'll just check.
Yeah,
Just a moment. Thank you.
yeah. So XPPT not the only one. There are some other softwares also, but I think it's very easy to do and it's very fast. I see someone has said me that. So if you have any questions, just turn on your switch on your mics and ask me.
Yeah, sir. Now it's working. I just restarted the
Yeah,
Xping server and now it's working.
yeah. So has everyone like able to at least run the software? In software, there are lots of differential equations. If you go to the OD, there are thousands of OD equations written there. I just showed you the simplest ODE, that's a pendulum. I think Abdul Basit is trying to say something, so I don't actually
Uh,
get what he was
no,
trying to
actually,
say.
she was asking a question in chat. I was just responding to.
Okay.
There was a question in chat.
Oh, okay. Try searching and start by pressing Windows key and search Xpring. Okay.
Yeah, sir. Can you just show the graphs again? Like, can you just do how, like, you got the graphs?
Oh, okay. Okay. Let's erase it and go to the initial conditions and just type go. That's the only thing you have to go. No, do
Okay, initial conditions and then
initial condition and go. Go
go.
is yeah.
Okay.
Go is like every time you will get a graph. So I changed the axis. Let me change the axis to a little bit more lenient. So now I set the mu at 0. So it will give you my like undamped pendulum oscillations, simple periodic oscillations. If your mu is 2.0, that is there and by default, you will see a damping oscillations, not a periodic oscillations like mine.
Yeah.
And I also changed like x versus t, right? So this t is there. So for phase plane, just write x, and here y-axis write xp, and say some x mean minus 4 to x mass. Let's keep at 4, y minus 8 2 plus 8. and if you said okay, you'll get a periodic solutions. But it's for mu is equal to 0. I already kept mu is equal to 0 now. And for flow, you can type flow, you see the flow. And how I get the mu is equal to 0? Get the parameter here, right? Sometimes it doesn't work for me also, but let me try. You see, now it is a spiral.
Okay.
If you just type 2, not a periodic oscillation, but a spiral.
Okay.
Has everyone got it? Even if someone is not familiar with this software and all, they can just go to the notebook and run the codes. It will give you the same output. Is it okay for everyone? Should I move on? Still, some people need some clarification. Okay, I'm waiting for 2-3 minutes. Then I'll go to the next steps. So I sent you one MATLAB app, that is you can see .ml app. And if you have MATLAB, then it's okay. You can run this app in your MATLAB, in your app column in MATLAB. Like if you go to MATLAB, just see there is apps. You can run those in the apps, right? In case you don't have the MATLAB, I think often cases people don't have the MATLAB, so you can go to this MATLAB online. So this is the file that I sent you, final of app.ml app. Has anyone got the MATLAB app? Run it on MATLAB or the online version of MATLAB.
Yeah, which link or what are we supposed to do in the MATLAB?
Oh, okay. So have you seen this file that I sent you, like final hop app.ml app .ml app file? Have you got it?
To be honest, no. Where did you send? I'm not familiar with it.
Okay, I think I sent you guys this file .ml app. It should be there in the drive. Have you got it?
No, sir. Can you share the link or something? I'm completely lost where it.
Okay. How can I share it? Let me try to
Like
share it.
if it's code, you can put in the chat. Like, is
No,
it
no,
like a
it's
package?
it's kind of package. It's kind of app
Okay.
written in MATLAB.
Okay.
So how can I send you? I think I sent Sundari so that you guys can have it.
Yeah, we got the collaboratory links, and then you sent a link in the morning for the XPP. Other than that, I couldn't find anything else.
Let me check. Um, okay. How can I send you now? Okay, let me send by WhatsApp. I think that's the easiest way to send you. Just wait for a few minutes.
I think Anirban, you can share the drive link in the WhatsApp. Huh?
Yeah, that's what I'm trying. This drive link. Yeah, that's a good idea. If you open the drive, you'll see that
Anirban, it is asking for access.
okay. So if you open this file, this ACCS 2023 file,
Mm-hmm.
you'll get this final hop app.ml app.
Okay.
This one. So you can download this.
Sorry, where is this shared?
Oh, it's shared in the Zoom chat.
Somebody's also put it on the WhatsApp group. So you
Yeah.
can find it there as well.
So you can download it and open it in MATLAB. If you have already installed MATLAB, you can just click it. It will open your MATLAB window and run it. Then it will ask you to run it. Click the run button, it will run.
Yeah, now it's showing on the left side of the files in MATLAB online.
Yeah. So are you using the online version?
Yeah, yes.
Yeah, it's showing here, right? If you upload
Yeah,
here,
yeah.
file.
Yes.
Okay, good. Then just click it. It will take some time because it is a little bit slow. This online versions. Then you can click run. So you see this app. So I only talked about the three types of couplings that is there within the hop oscillator. That is real, complex, and power coupling. So here there's two oscillators. We try to give some intrinsic frequency to the oscillators. Let's say we'll give some frequency 0.01 and frequency 1, and frequency 2 we try to give 0.01 and give some real weight and just submit. Well, let's 0.1 is too slow. Let's say we have 0.1 and 0.1. You see the phase difference if we give the frequency at same frequency 0.1 and 0.1, so hertz or radian per second. Then it will give the steady state phase difference. Phi 1 and phi 2 after some time, it will be at the steady state. Right.
Yeah.
Even you see more interesting phenomena, if you increase the strength up to 0.2 and click it, see how fast it's going to the steady state phase, right? And if you increase the knob little bit much further, at 0.3, and submit it, you see
Okay.
it's going much faster at the steady state.
The time required gets lesser
Yeah,
and lesser.
yeah. Let's say we have 0.3 and what we change the frequency. Change the frequency 0.3. Then you submit it. You see the phase difference vanished. Even if we increase
Yeah.
the strength 0.4, it's not going to a steady state phase difference. So that is the problem with this real coupling. Even let's say we go to complex coupling. In the drop down menu, we can go to the complex
Mm-hmm.
and keep the frequency, let's say in 0.1, 0.1, submit. It's a steady state phase difference. So the phase difference we see in a complex coupling as a phi 1 minus phi 2 minus theta. That will be a steady state. We
Okay.
can just change the strength also and see. It's nothing but the different solutions of the different initialization. What is a steady state? Right. Now, in the drop down menu from complex, if you go to power, and let's say we are now at a now we go to the power coupling and submit same frequency. For the power coupling, the phase difference is the phi 1 by omega 1 minus phi 2 by omega 2 minus theta by omega 1 into omega 2. This normalized, we call it a normalized phase difference.
Okay.
So we'll get a normalized phase difference and it's steady state. But see if we increase the frequency 0.1 to 0.5 and submit, it's still a steady state phase difference after some time. Even if we increase some 0.5 to 1, see after some time it's capture the steady state phase difference. To see how the steady state phase difference occurs in different kind of strength, right?
Yes, sir.
Even different strength, go different strength. So that tells you that how you can couple these two hop oscillators which have different frequencies like 0.1 and 1 and still having different frequencies, they're having a steady state phase difference given by this normally steady state phase difference because we are taking the frequency term in the oscillator equations, right? This is a very easy app, very easy to understand and interactive also. I hope you guys are trying it with me. Try to see. If anyone doesn't have the MATLAB, they can simply open the online MATLAB, log in by their mail ID or the institute mail ID, and drop this final hop app .ml app there and try to see how the change happens. Change the knobs and drop down menu. You can see different types of couplings.
Like, is there a point after which this rule breaks, or it just continues and the value gets bigger, the bigger current we supply to it?
So if the frequencies gets bigger,
Mm-hmm.
then we find there is a problem. It's much bigger. Let's say 0.1 and 100. Sometimes
Mm-hmm.
it gets problem, but
Okay.
if it's in between a range like 0.1 to 4, 2.1 to 5, the ratio
Mm-hmm.
is if the ratio is not that big, then you'll get a steady state phase difference.
Okay.
So in the I'll send one paper and share with one paper with you guys when we give the kind of tutorial notebook. In this paper, you can read how we implemented this power couplings. So, do you have any questions? Has anyone facing any difficulty to like implementing the MATLAB app or opening the MATLAB app?
It's added only when I don't even know why I need to add one.
It's adding one more paper. It normally remove
I'll wait for a few more minutes, and in between, if you have any questions, please ask me. And after that, Rohan will start his presentation.
It's not even wrong. I don't know what is possible when I do.
decoded that
Hello.
Hi.
Yes, sir. Sir, in case of Linux system, so I have installed the XPPUAT software, but how to locate the pendulum kind of program?
Okay, so
Where is the program? How
okay,
to find?
got it. So if you have installed it, so it's a similar thing. If you have installed it already, there is a file in OD in XPALL file. If you go to that file, and there is a OD.OD file called pend.od. Let me write down pend.od. So in this pend.od file, you just open the file. And when you open the file,
So where to search this file? Means in which menu I have to locate?
it's in OD.
Okay.
OD. Let me quit for now and let me show you. Let me quit it and let me show you once again. So I'm running from here. You see, there's a OD file. So you have to locate XPAll. In XPUT, you have to locate XPAll, and then by CD or some directories from the terminal, you can go to this OD folder. Go to OD folder and just type pend.od. It will give you this this pendulum OD. See, there is a spirals because it's a damping pendulum, and as I told you, you see the equations. Yeah. Have you got it?
Yes, sir.
Oh, great. Please ask me if you have any questions. Otherwise, I will exit, and Rohan will start his presentation. I'll wait for 2 more minutes. So, if you have any questions from the installations, XPUT softwares, or MATLAB app, let me know.
Hello.
Hi.
Sir, I have a project that is oscillation of brain fMRI. So, what will be the project about? Means how? What are the tasks we should perform? Can you please tell me? I was told that I was assigned to you only.
Okay. So there, I have a oscillator model for the fMRI, and we'll discuss lots of computational model that is already available to understand the fMRI data. So we'll talk about the different kind of models for fMRI data, function connectivity, structure connectivity, and how our model can overcome all the caveats that were there in the earlier models. So we'll do a little discussions, and then I'll ask you guys to implement those kind of ideas in some of your projects.
Anirban, is XPP app important for that? XPP out?
No, I don't think it is important.
All right. Okay. Thank you. Because I'm having some trouble installing it.
No,
Yeah.
it's not
Okay.
at all important.
Okay.
What is timing during the implementation?
Timing we'll discuss with you guys, and then we'll see that what can be implemented within 2 days.
No. Not a 2 days, about 2 hour. I think timing is the discussion is about 2 hour. I think.
From 2 o'clock to 4:30.
Yeah.
Okay.
Either
4:30.
day 4 or day 5. Yeah.
Yeah. What is the in the 2 point? I think 2.5 hour.
Yeah.
About I think you have divided into too many groups. Am I right?
Yeah.
But I think I have to come on Zoom meeting and implement, I think, directly. Am I right?
Yeah, I will go through the codes. Then first you have to understand the codes. Then you want then I will talk with you guys that how you want to implement the codes by yourselves. Then you can implement those codes to come up with an idea that how you can implement the codes for your projects, for your ideas.
Okay. Okay
Yeah,
then.
yeah.
So the code will be based on the MATLAB or Python?
So earlier I had the MATLAB codes, but now it's converted to Python totally, so that everyone can run it. I find that many people doesn't have the MATLAB nowadays, so I'll share the codes in Collabs, and from the Collabs you can run it.
Okay, thank you, sir.
Yeah.
Can you share those Python material earlier so that we can look at it and have a better idea before the session?
Sure. Before the session, I will share with you guys.
Okay. Thank you.
Yeah. Okay, then so I'm stop sharing, and I think Rohan will now take over this, and he'll share his screen.
Hello, I hope I am audible and you can see my screen, specifically the slide.
Yeah, we can see.
Thanks, Anirban. So, good afternoon, everyone, and thank you very much for enthusiastically participating in this workshop. As sir, towards the second session, he talked about how oscillators are being used in our lab for brain models and building large scale models. So this is a brief introduction about how we can do it and some initial codes that we can just to get an experience about how networks of oscillators can be used for training and like a neural network and how they give rise to some biologically important phenomena. So let's begin. As we have seen now at this time and multiple times, this is an oscillator on the left hand side and on the right hand side. Different types of oscillators. This is a harmonic oscillator, which is the hop oscillator that we've been concentrating on. And this is what is a relaxation oscillator, or the oscillators that we have seen with the neuron models, specifically Morris Lakar or Fujinogama. The amplitude is the difference, and the time period is the difference between the two maximum states. So as mentioned, that we are looking at ensemble activity of neurons, and that can be best modeled at the hop bifurcation. And this is an idea that has been suggested multiple times at various stages in the last couple of decades, uh, beginning by, of course, Bazaki, and then multiple other people have also mentioned, even recently, as more and more papers are being published on this. The idea is that neurons work at the critical hop bifurcation. All right. So we'll go to that. Just to give an idea, the two phenomena that we'll probably be noticing now is the so uh, the various functions that the brain sort of affects or sort of does can be characterized into four of these into minimally four of these informations, which is synchronizing neuronal assemblies and input selection of frequency selectivity or resonance. Sir touched upon resonance quite a bit in his study, in his lecture in the morning. And the synchronizing neuronal assemblies also was kind of touched upon, and I will sort of give a brief example of how we can notice such things. The other two information I assume can be are actually part of the workshop in some way or the other in a very abstract sense. And in future, our lab is trying to continue bridge the gap between oscillators and all the four informations. So the four types of brain functions that have been mentioned here have been taken from Buzaki and Raghu's paper on neuronal oscillations and cortical networks. So I suppose this image or this kind of an image is now familiar to everyone, especially after the workshop, that this is a neural network with successive neurons and weights and neurons and weights and successive stages of those. The only difference now we have is the fact that that the alternate layers are either static traditional neuronal the neural network units that you may have studied up until now, and the other stages of them are the neural oscillators. So the oscillators that we are considering are going to be Hop oscillators that has been described by Sir in detail as well as by Anirban, but yet I will give a small idea of what these are. So motivation as to why Sir already mentioned, just to touch upon that base, is that the biologically inspired oscillatory models can capture brain like rhythmic dynamics, but they do not capture these dynamics as a phenomena that emerged out of input-output relation or behavior. So, for example, if we are doing a particular task, the data that is being recorded that shows these rhythmic dynamical behavior is like it happened because the task was being executed, and removing the task input and output behavior from the rhythmic dynamics is not exactly how we should be able to model it. And the fact is, these rhythmic dynamics emerge as a natural phenomena when we are trying to execute a particular action, for which a lot of data is being recorded. On the other hand, as you may have seen, deep neural networks do not have this natural brain-like, the neuronal oscillation at least. Although we have seen various other phenomena that neural networks are able to capture from neuroscience. The rhythmic part of it has not been explored as well as yet, and that is how we are trying to bridge the gap from neural networks to the oscillators by constructing such oscillatory neural networks and suggesting them as probably the ideal middle ground, which can bridge behavior as part of the rhythmic dynamics, not parallelly or not independently suggested or studied. Sir gave a very systems level approach to this. Sir gave a very systems level approach idea to this. I would also like to give a very individual or a very fundamental idea of how frequencies are relevant in individual neurons as well. So, for example, on the right hand side are actually the activities of two olivary neurons that are in the inferior olive, and both of them are of the same patient or the same human subject, and one is oscillating, the other is not. Okay, but they have the same resonance profile. Both of them, even though one is oscillating, the other is not, prefer the 4 Hz or around 4 Hz frequency. They have the highest response there. The highest amplitude is there. So this is even at individual neuron level, there is a preference for frequencies. So why does this become of importance? As the information is being propagated from one side of the brain to the other, or from across the neuronal population, the neurons will have their own will affect the population activity in their own way, and neurons that are selective towards one particular frequency will be most suggestive or more amplify that effect more often than other neurons. So which will give rise to various kinds of brain phenomena and the behavior and the phase amplitude and the amplitudes and so on. So that is why this was mentioned. We just saw Sir mention, and as did Anirban, the Hop oscillator equation in polar coordinates is given by this. Okay, and as you can see here, when the frequency difference between the input and the oscillator's own frequency is 0, then the response is maximum. Otherwise, you see all sorts of behavior. So at this point, maybe we can look at the first Colab file, which is mathematical models. So this already has been covered, but I just wanted to introduce. So what we have here is effectively the Hopf oscillator equation in the first cell with some introduction and so on. We have some. So this is the Hopf oscillator equation in complex domain. And the rest of it is just so that we can simulate the ideas. So I'm not going into detail. Anirban has already discussed this primarily, but these are the libraries that are required: the Torch, NumPy, and so on. The Hopf dynamics is actually the Hopf oscillator differential equation. RK4 is a numerical technique that Anirban mentioned that can be used to solve such differential equations. Okay, so just to show, you can open this and run this file and run the code till here, and you can play around with the parameters. So if you go from from right now mu is initialized at 1. If you were to go to mu less than 0, then the oscillations will stop. So just to show the fact, let us run this. Give it a few minutes as it's trying to connect. So I would recommend that you can also run these files, in your own personal computers. They're Colab folders. Nothing needs to really be done. Just open it and start running it. So now that this is run, you can interact with this. So for example, if you notice, if I were to put mu less than 0, which is minus 0.1, and after a while, this will stop oscillating and start dying down, giving rise to a spiral, right? So let us reduce it even further. The oscillations have died down completely, right? And if you notice anything, if it looks like it's still oscillating, it's because the scales are really small. If you see, it's e to the power minus 44. So this is to show the fact that the oscillator stops oscillating after a while if mu is less than 0. And of course, if mu is greater than 0, then it'll start oscillating. Give it a few minutes. Yeah, start oscillating again. Okay, if you look at the next cell, which is experiment B, which is phase space trajectories, one peculiar phenomena, if you look at the two pictures on the center picture and the one on the right, is just to show the fact that if the frequency is away from the natural frequency, the frequency of the oscillator in this case is 5 Hertz. I hope you did notice that. So omega naught is 5, right? So after running this differential equation, you can see that when omega is equal to 5, omega naught is also equal to 5. There is a higher amplitude. The natural cycle is where if there was no input into the system. And as we start giving input at the same frequency, the amplitude is higher. On the other hand, when the frequency is off the resonance peak, it is omega equal to 2, then we see that the oscillations are no longer clean and the amplitude is suggestively small. So for to get an idea of how the frequency and this, you can run experiment C. It'll run really fast, and you can see that at 5 Hertz or at 5 omega, the response of the oscillator is maximum. That is, the amplitude is highest, right? And as we go away from 5, the amplitude starts reducing quite drastically, and eventually kind of plateaus around this while to about 1 Hertz. Okay, so this is the Hopf oscillator and the two properties that I would like to highlight. One is the bifurcation parameter, and the other is the resonance property. Okay, so if anybody would like to have a theoretical, if anybody is interested in the theoretical understanding of how such things can be calculated, you can look at this paper on the bottom, which is signal processing and periodically forced gradient frequency networks. People have suggested, research has suggested that neurons have multiple resonances, not only one. and for which such a differential equation can be used to have multiple resonance peaks. So if you notice, it has a primary resonance at 1 hertz, a secondary resonance at 2 hertz, and a subharmonic resonance at 3 hertz, at 3 omega. Just to show the fact that there are oscillators that have resonances at multiple frequencies, not only at the primary frequency. So, and as you have noticed, neurons that we have studied previously in this workshop have very complicated activities and properties. Each has a different preference to a frequency. So just to reinstate, how do we solve this? Because we need to solve such differential equations. In the Colab folder that we just saw, I'm using a fourth order method, which is called Runge-Kutta, and it has a very sharp convergence rate to a solution. But for a simpler equation, we can also use what is called as the Euler update rule. Okay, so what is that? We basically write dr is necessarily the differential change in r, which can be written as Rn plus 1 minus Rn. So if you write Rn plus 1 minus Rn and delta t on the bottom, which is equal to h goes to the right hand side and Rn plus 1 is equal to Rn. So by iterating over this for n tends to infinity, we will see that we can get a solution to this differential equation, which is what you're seeing in the Colab folders, okay, up until now. Okay, so coming back to Dawn, what we had as two successive layers. So there is an input layer, there is an oscillator layer, and there's a nonlinear layer, which is traditionally TANH or a ReLU neuron that you have studied previously in the workshop. So as the oscillators run, they will produce an oscillatory signal like this, which is given in this portion, right, which is highlighted in this green shade. This is the oscillatory activity that is being generated at each oscillator, as we have seen. This oscillatory activity is received at each of the neurons in the next layer. Okay, they get multiplied by this edge here, which is a weight W, and the nonlinear activation is applied pointwise. Okay, so for example, if you have sine omega t, then TANH or ReLU is applied to each point of the signal. So at each signal, at each time step that we have the solution from, TANH is applied to it. Okay, so this is the feed-forward propagation. Input comes in, it runs the oscillators. The oscillators produce a signal like this. This gets multiplied by some weight and is received at the next layer. Okay, that is feed-forward propagation. So previously, people might in the workshop might have said about how we train such artificial neural networks. So training also will be involved here in this case. And the training is a bit more convoluted, little bit more complex. And there are two possible ways of doing it. One is called the back propagation through time, which is in oscillators. So what is going to happen? We solve the oscillators as we saw in the Euler update, which is this. We solve the oscillator and we get ht minus 1, ht plus 1, ht plus 2, ht.
Hello.
Right. Hello.
Sir, in the previous some of the previous slide, you shown a figure where there is a ReLU unit, then there is a oscillator unit.
Yes.
Right. Yeah. So in this neural oscillator unit, so how does it work? I think you have mentioned right now, no?
Yeah. So each
So
of the
can you please repeat once again?
repeat? Yeah. So this is a traditional neural network with successive layers, right? One after the other.
Yeah.
What we have done is we've replaced every alternate layer with an oscillator. So what does that mean? So there is an input coming in, some input, which could be a signal, it could be an image, it could be any vector that is coming in, as you have seen in the previous workshops sessions, right? When you were doing simple deep learning strategies. An input is coming in, that input is sent to the oscillator layer. So what happens in the oscillator layer? So the input will be some function of time, which is I of t. Okay. It could be an image changing in time. It could be a vector. It could be a signal. It could be some sine omega t that is changing in time. And that signal, after whatever happens in the previous layer, is received at the oscillator layer, which is I of t. Okay. So I of t, if I of t is given by this, then the differential equation is written in this form. Okay. And once this differential equation is written in this form, this equation is solved using Euler update rule, as I just discussed, and you get a time series, right? If you notice, So you will do this. Rn plus 1 is equal to Rn. So you will get R, R1, R2, R3, R4, Rn plus 1, so on, so on. You'll get a long history of over time about what R value becomes. So this is a time series. Okay. So this time series is the solution of this differential equation, where this is basically the output of the oscillator. Okay.
Okay, sir. Okay.
So this oscillatory activity will look something like this, right? It will be some oscillations, some going up and down, right? And this oscillatory activity, now in a neural network, the information has to flow in a feed forward direction, right? Then you train using back propagation. For the feed forward, now you don't have a single vector, you have a time series. So this time series gets multiplied by weights, okay, and is received at the next layer, at this layer, which will have some other oscillator or a nonlinear layer. It could be ReLU, it could be tanh, okay, and it'll operate on the time series as expected. Okay, so just to again recap, input comes in from some layer previously. It could be a signal, it could be a vector, it could be an image. That goes to the oscillator layer as I of t. The I of t differential equation looks something like this. And this differential equation is solved using Euler update rule. Once you solve this Euler update rule, you will get a time history of R1, R2, phi1, phi2, phi3, R1, R2, so on. So you'll get a time series. This time series will look something like this, which is the green shaded area. Now this time series is then sent as in the forward direction to the next layer. Okay. Previously you had tanh activations, now you have oscillatory activations. Think of it this way. Now this is a feed forward. You also have to train the network. So what is happening? So input is coming in, which gives us various stages, ht minus 1, ht plus 1. Okay, and you calculate some loss. Now the loss has to be back propagated in time. So this is what effectively we are trying to show here. And the gradient accumulation function looks something like this on the left hand side. So just giving a brief introduction, this is how it happens. For more details, we might have to study it separately. But just to give an idea that as the information is flowing forwards by xt, xt plus 1, ht plus 1, similarly, the error also flows back in time, which is given by this equation, or in equation number 2, gradient accumulation. So finally, del L by del W is the gradient accumulation over all the time. Okay. So this is the idea of training such networks. There is an alternative method, which is a bit more mathematically involved, which is called as adjoint sensitivity analysis. So what they do here, instead of doing one after the other this time series, they can integrate two differential equations, which is given by equation 1 and 2, and the gradients can be calculated very fast. That's the idea. So, and the advantages of this method are the fact that it is memory efficient, it is time efficient, and it can calculate the gradients in a very parallel fashion as we've been doing for the previously. So this is a bit more involved technique, and this will require some study material that maybe we can share later if you are interested. I'm not going into too many details. The advantage with modern day implementations of neural network is nobody has to do any of this. The automatic differentiator for each library does it for us. That is the advantage. So let's look at some results. So the first result is a very straightforward input-output phenomena. What we are doing here is, if you look at the, let me zoom in. If you look at the dotted line in the background, that is the input, okay, to the neural network. The output should also be the same is what we are trying to train the network for. So the output is given by this red line. Okay, as you see, it is more or less matching. There are two types of signals that we are training for. One is a simple sinusoidal signal, which is given by the top figure, and the other is a chirp signal. So what is the difference? The chirp signal has, as time goes by, the frequency increases in time. So as you see, the gap between this layer, these two peaks, is smaller than these two peaks, is larger than these two peaks. So the frequency is increasing in time. Okay, so for this, you can all open the second Colab file, which is Dawn autoencoder. You can also run it, but at your own time. But here currently, I'll just show the results that are already run for you in this case. So I'll go through the code cells. Again, as usual, we are importing some libraries. These are from Torch. Torch is a very famous library that is used for neural networks. We are generating two types of data sets. The generate sinusoids generates the sinusoidal frequency, which is given by the signal here. And the chirp signal generates a generates a signal whose frequency also increases in time. Here the frequency will remain constant. Here the frequency continues to increase. So that's the difference between a chirp signal and a sinusoid. Okay, the rest is just to construct a data set, and all this is wrapper so that we can train the model. Okay, so that is cell number 1. And cell 2 is actually the hop layer. So what is the hop layer? So if you notice, the hop oscillator has a couple of parameters. One is omega, one is mu that we already saw, and the other is beta. Okay, so we need to initialize those values. These are initialized after running it for long times and everything. So here we run. So the omega parameters are defined. So these so they are defined linearly between some small omega and a large omega, min omega or max omega. Okay, these are the parameters. dt is h, the amount of time for which we are calculating the next Euler update. Okay, and the forward propagation is basically we are solving the differential equation in this loop. So if you are interested, you can read through this loop again. But for now, what we are doing is basically solving the differential equation using the Euler integration loop. Okay, what is happening? The for loop runs for time, for a sequence length. As it runs, we will see the R values and the phi values are getting updated. So delta phi is some value this, phi t is phi t plus delta phi, is the Euler update rule. Similarly for R, and this history is stored in R history and phi history. Okay, then all of this is so that we can do the neural network. Now after the signal is constructed, we calculate the Cartesian coordinates, the signals, because after R and theta, we get the cos omega t and the sin omega t, R sin omega t, R cos omega t. This is the hop layer. This is the oscillator autoencoder, which is effectively the neural network that we are trying to train. So what does this have? This has an input, which is one-dimensional signal. It has some number of units depending on whatever we choose. Okay. Then there is an oscillator layer that runs the oscillator for the frequency and the input signal, and there is another layer to decode the output. Okay, and finally the output is given here. So the next cell is actually to train the neural network. If you were to run it on GPU, it'll run really fast. Maybe in maybe a minute or so, it can give you an output. And as you see, the loss decreases in time, 0.33 to 0.01. That is what a neural network should do. Loss is mean squared error. And this is a training loop. So what we have, we needed the number of units. We put 50 units. We wanted to train for 20 epochs, so we have 20 epochs, and we have to give a learning rate for the weights to be updated. Okay, the model, as we call it, calls the model that has been defined here, which has got hidden nearness 50, and the oscillator frequency range is 1 to 20. Now, why did we choose 1 to 20? We chose 1 to 20 because here, when we generated the data, we chose a frequency from 5 to 15, right? So we want the oscillators to encompass the frequency that is coming into it so that we can have maximum information. Because what are we trying to do? We are trying to use the resonance that we have shown for hop oscillators to be able to do the intelligent tasks for us. Okay. So we have the frequencies from 1 to 20 hertz, 1 to 20 omega, that is. Okay. So after the neural network is trained, the next cell is so that we can look at some outputs. And so here what we do, we have a test signal, which is some sinusoid, and a test chirp signal, which is some chirp signal. We'll pass it through the model and look at the predicted outputs, the sine and the chirp signal. So what we are trying to do here, the input and the output should be the same. So we are basically trying to reconstruct the input. And as you see, this is the code that has been run already. And you see that the signal more or less matches it quite well. Okay. If we train it for longer periods of time and for more oscillators, the performance will definitely improve. The first one, the red signal, is for the sinusoid, And the blue signal is for a chirp signal, where the frequency is increasing with time. As again, here the frequencies are smaller, and as time goes by, the frequencies are larger. Okay. So this is to show the neural network performance. The next cell is to inspect what is happening to the oscillator. So what we have, so this is our neural network. There's an input, there's an oscillator, there's an output. So we want to see what is happening to the oscillators, right? Because that is where all the intelligence and the oscillators are being trained, and the oscillators are receiving input and output. And we want to see what is happening to the oscillators that the neural network is able to perform. Okay, this is basically we are trying to understand how the neural network was able to do this. So if you were to run these cells, it will use the weights that were trained for this neuron, for this layer, and it will try to give us plots. So let us look at this plot. The first plot on the top is the output. So we gave it an input chirp signal, and it reconstructed the input chirp signal. Okay, so this is what we want the network to perform. It should be able to reconstruct what we want to do. Secondly is the activations of the oscillators. Okay, as I said, the oscillator runs, it solves a differential equation. The differential equation gives rise to such kind of signals. And if you notice, let's look at this gray signal over here. Its amplitude is low in the beginning. Slowly it increases and then again reduces, right? Similarly, if you look at this, the red signal amplitude also increases and then starts reducing and then starts increasing again. Okay, so what is happening is, as the chirp signal comes in, because the frequency of this is not constant, right? It is increasing in time. It is activating different oscillators in the layer. Okay, and what do we mean by activating? The oscillators activations, the amplitude of the oscillators are increasing in time and then reducing. So particularly taking the example of the gray signal, as the input comes in, the frequency in the middle at some time between maybe 400 to 800 time steps, the frequency is equal to the frequency of the Hopf oscillator of the gray signal. So that is why its amplitude increased, and this we saw as resonance behavior, right? And as the frequency kept increasing, the resonance reduces again after time, right? So this is how the neural network was able to perform. It is learning of the behavior of the oscillators. So looking at another example, the red one. The red one maybe has a frequency which is in this range. Somewhere here, the frequency of the signal is equal to the frequency of the Hopf oscillator of the red signal. That is why the amplitude is maximum in this range, and it reduces. Correct? So this is the behavior that we are trying to, this is what Sir was talking about, the internal resonances of the continuum, the continuum medium of the brain. And effectively, this is one way that we hypothesize the information is being, captured and reintegrated and, sort of processed so that we are able to learn various tasks. So the next two pictures, this is a face portrait. So it no longer has a very clean face portrait. Because of the input, the oscillators are doing all sorts of weird behavior. Okay, this is on the right-hand side, the face space. On the left-hand side is a summary plot of the oscillators activations. So if you look at this neuron 14, for example, which is probably 14 or 13, it has the maximum amplitude, right? The dark blues are the bluest or the darkest, and the light greens are the lightest. This has highest amplitude. This oscillator is probably oscillator which is gray in color over here, because it has the maximum response. And as you see, initially the amplitudes are low. Slowly the amplitudes increase, and then start reducing again, right? So this is a summary plot of all the oscillators. Here we looked at a few oscillators. Okay. So this is what we are trying to say. The neural network was able to do this task, that is to reconstruct the input, okay, by learning of the frequencies that are coming in. Those oscillators tend to increase their amplitude, and the oscillator and the neural network was able to reconstruct the input. So Effectively, what we are doing here is some kind of Fourier analysis. Wow, the oscillator's frequencies have some frequencies. As the input comes in, if the frequency matches, the oscillator's response is higher. Based off of that, the neural network is able to reconstruct or do the task. So this is an autoencoder, very, very straightforward task. Let us look at another straightforward task, which is a classification task. Okay. So here we are trying to do a signal classification. So now problem is, in a classification, we need a label. So up until now, the labels that we have been seeing in neural networks are 1, 0, 0, 1, or they are one hot encoded where the symbols are given by 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, so on, so on, so on. So, but problem is with the oscillator, the output is always going to be a time series, right? As we saw, in the previous here, the oscillator is always going to be a time series. Therefore, every output after that is going to be a time series. So what we do to classify is the following. So let us take this example on the left-hand side. We have two examples, one on the top and the bottom. The top is a higher frequency than on the bottom, which is slow frequency oscillations, right? The idea of the neural network is to classify between high frequency oscillations and the low frequency oscillations. Okay, that is the neural network task that we are trying to train for. Now, how do we say that this the fast frequency is class 1 and the slow frequency is class 2? What we have done here is the neural network should map the faster frequency to a slope to a signal like this, where the blue one is increasing and the orange one is 0, and the slow frequency the opposite. The orange one is increasing and the blue one is 0. Okay. So we have 20 or 50 oscillators in this neural network in the hidden layer, and the classification activation is given by this. So we train the model, and let us look at the code file. So for this, let us open. It is called
Hello.
Hi.
Yes, sir. As for the previous code, is this kind of model is applicable for the EEG signals for the
Yes.
epileptic kind of patients where the
Yes,
seizures
yes.
can be predicted? So
Yes, yes.
you have mentioned this is as a autoencoder type of things, isn't it?
Yeah. So
So
autoencoder is just to give an idea of how the neural network works. But if you look at our paper we will share all these papers, after the session today, and we have trained for EEG signals directly. Okay, where the neural network was used to reconstruct EEG signals predict EEG signals, reconstruct EEG signals, classify EEG signals as epileptic or normal. So we
yes.
have used
So
the same network, exactly the same network, but for those kind of tasks as well.
okay. So did you get the performance? How the performance was it? Means is it it is giving better accuracy kind of
We
thing?
were able to show better performance on EEG, on classification of EEG, and specifically we were able to show better performance primarily on reconstruction of EEG tasks. So I will share that paper. You can have a look at it. And
Okay, definitely.
yeah, so that was one of the advantages, and that is what is being used in our lab from now onwards. Because the other advantage, as sir, if you remember in the lecture mentioned, that we have fewer parameters that we need to train in this network.
Okay.
And
Okay.
and there are a few other advantages as well, so which maybe I will touch upon towards the end of the session. But with this code that you now have available, right, the code that we have shared here, this exact code can be used for any task that you want. Only thing you need to do is change the input and output and the data set. Okay.
Okay.
Yeah.
So please, sir, share the actual publication so that I can go through.
We will do that. Okay.
Thank you.
Okay. So the next collab, if I can, is temporal sequence processing. Sorry. Okay. So let us look at this. So this is, again, we are doing the same thing. We have a hop oscillator. Okay. We have this data set. So I am basically repeating what is happening here. So we have these two data sets. We have a data set which has two classes, a faster frequency and a slower frequency. And these are the classification labels. If the frequency is faster, then the blue label should be high. And if the frequency is slower, then the orange label should be high. So this is what is called as a ramp kind of an output classification, which is kind of biologically plausible. And people have shown in various studies how this is kind of behavior that is seen before a task is executed or a classification label is assigned in the brain for tasks that is performed by human subjects. So let's look at the code. So again, first cell is some libraries and everything. Second is generating the data set. And this is just showing the data set. Again, there's a faster frequency and a slower frequency. The slower frequency, the blue label should be high, and the faster frequency, orange label should be high. This again is the oscillator loop. You can look at it in your own detail, but it's effectively doing the same thing. We have an Euler loop. We are solving the differential equation using the Euler loop. Once we have the time history, we send it forward. So this is a neural network layer. Input comes into a dense layer, which is the first layer, which is a nonlinear layer. The next layer is a Hopf oscillator layer with minimum omega 1, maximum omega 20. And the third is the output layer, which does the classification. So, if it's low frequency, then the blue label should be higher. And if it's a faster frequency, the orange label should be higher. All of this is wrappers so that the neural network can be trained using, in this case, Keras. Okay. So you can run this, it'll run fairly fast. And we can run all the files still here. And you should get something like this, which is the training convergence, right? So after about 30 epochs, the neural network is trained. The loss is really small. And we can stop training and look at the classification. Okay, so here the classification label is, because the task is fairly simple, then the neural network has almost 100% accuracy. And this is a simple depiction that the predicted class should the orangish label should be higher, and as you can see, the orange label is higher, and the blue label is below. Okay, so again, as we did for the autoencoder, let's look at the oscillators activation. So if you look at the data set, each signal has two frequency components, W1, W2. Okay, in the low frequency, and if it's a higher frequency, then there is W2, W3, W4, again two frequencies. So as per resonance, there should be two peaks in the oscillatory activations, right? Because of the resonance, oscillators that have frequency closer to the input will have higher response, and oscillators away from the frequencies will have lower response. So this is what we expect, as we have seen in the resonance. And you can see when the input is from the lower frequency side, the lower half of the oscillators, there are two peaks, right? So just to describe what this is, what we did, we ran the we took one of the signals. So let's say, for example, in the first case, we took the blue signal. We pass it through a trained neural network. Okay, we pass it through the trained neural network, which is layer 1, layer 2, layer 3. We look at layer 2, which is the oscillator layer, and look at its oscillatory activity. Okay. Now, in the previous case, we saw the oscillatory activity, how the amplitudes were increasing and reducing in time because of the signal. Now, what we are going to do is we look at the average amplitude of the oscillators. Okay. And the average oscillator amplitude is plotted here. So we have 50 oscillators as mentioned here. So we have 50 oscillators, which was mentioned right in the beginning, I think here. Sorry, how many? Yeah, we have 50 units, 50 oscillators. Okay, so therefore there are 50 indices here. And on the y-axis is the amplitude of each oscillator that we have plotted. Okay, so as is expected, when the input is of lower frequency, the lower half of the amplitudes are higher. There are two peaks as expected. And when the frequency is higher, then the second half of the oscillators have two peaks, right? Here and here. So this is what the neural network is using to be able to classify. Because effectively what is happening, the amplitudes show this differential behavior with the input and the output, based off of which the neural network is able to classify. This kind of behavior has emerged, and this is the kind of behavior that Sir showed in the cochlea experiment, right? How there is a membrane, and each part of the membrane has preference to different frequencies. Similarly, consider this membrane from the left to the right. On the left, the slower frequencies have the oscillators are of lower frequency, therefore they are sensitive to lower frequency. And on the right, the frequency of the oscillators are higher, therefore they are sensitive to higher frequencies. And that is why when we give a signal which is of lower frequency or class 1, there are 2 peaks in the lower half. And when we give a signal in the class 2, which is of higher frequency, then we see two peaks in the second half of the oscillators. So this is effectively working as a cochlea, but in a very reduced order form. Okay. The other 2 are summaries. As you can see, some oscillators show different kind of behavior. So just to see, we look at 5 oscillators, 0, 1, 2, 3, 4. And I gave it 50 inputs. Okay. So for different inputs, so for most of these kind of inputs, there is small activation here. The oscillator 0 has highest activation for input number maybe 15 or maybe 70. Just to show the fact that they have this frequency preference. Each oscillator has this frequency preference, and that is what is being used to be able to classify neural networks, to do the classification task. Okay. Let us look at one more example. Sir mentioned this in his study as well, which is, effectively we are performing a definite and an indefinite integration. So what do we have? We have signals which are sine omega t plus pi by 2. So if we want to do an integration, then integration of sine omega t is a by omega. Integration of cos omega t is a by omega sine omega t, and similarly the differentiation is so. Okay, with some minus sign and plus sign. That minus sign is taken care of by the minus pi by 2 and the plus pi by 2 thing. Okay, so the third code, I hope I did share it. The fourth one, that is. So I think I have not shared this. Sorry. Let me share this as well. So I hope everybody has received the link. And so this code here performs the differentiation and integration. So first, differentiation. So the blue one is the input signal, and the derivative of omega sine omega t will be omega cos omega t, or with the minus sign or a plus sign, depending on sine and cos. Therefore, since omega is coming from a range of 0.1 to 7, so the amplitudes tend to increase because the omega gets multiplied with the amplitude, right? Again, we construct the same neural network as before. Everything is the same. There's nothing actually different. And we train the neural network. You can run these code cells. And since the task is a bit more difficult, the losses do not reduce as much, but they are able to reconstruct the output, right? So please run the code files. It'll take a few minutes, maybe 2 minutes, 3 minutes to train. And once after training, you can look at these training convergence and the differentiation. Similarly, towards the end is the integration, which is this. So please run the code files, and if you have any problems, you can ask me. The training should take about 3 minutes, I think, if you're using the GPU provided by Colab. Okay. So the same code, nothing different. There's an input layer, there's an oscillator layer, there's a post oscillator layer, which is the next tangent, and there's an output layer. Idea is to do integration. If I give it sine omega t, for example, the output should be omega cos omega t for minus omega cos omega t for differentiation, and for integration, it will be different. No, omega cos omega t, sorry. Okay. So test sample 1, 2, 3 just show how the differentiation was performed and the integration was performed. And the integration was performed here. Okay. So this is the experimental task. Again, we are doing an integration and differentiation of a function over time, and it is able to do this task quite significantly well. Okay. Again, here we are not looking at internal activations, but the code has been provided for that. If you notice cells after this, it also plots the internal activations, the frequencies, and the phase portraits, so you can play around with these values. and look at all the oscillations that we show here. Okay. Finally, the code for this unfortunately is not ready, so I will provide it in due course of time. But the idea is to show what is called as temporal binding phenomena. So what is a temporal binding phenomena? So let us look at these videos. I hope you can see these videos. Okay. So there is a red color bar which is moving horizontally. Uh, okay, and there's a green color bar that is moving vertically. Okay, in this case. Similarly, we have red color which is moving vertically and green color which is moving horizontally, and each of them has a different speed. Okay, the classification task is very simple. There are four classes: red horizontal, red vertical, green horizontal, green vertical. And the idea is to classify if the video the bar is red and moving up or moving in horizontal, or if the bar is green or moving vertically. So there are four classes, two each for two features. Okay. For this, we constructed what is called as a convolutional version of an oscillator network. So the input video comes in, there's a convolution layer, followed by an oscillatory layer, then a convolution layer, followed by an oscillatory layer, and a convolution layer, followed by an oscillatory layer with a dense layer output. Again, we use the RAM classification. And what we show here, which is this figure on the bottom, is what is called as temporal binding. So what is temporal binding? Temporal binding phenomena is a way both spatial and temporal features are sort of compressed and processed simultaneously. Okay, so if this in this case, if the subject is looking at the green vertical or a red horizontal or a red vertical, each neuron will have some kind of there will be neurons that will preferentially encode for one particular feature. Maybe it is red in color, maybe it is the green in color, maybe it's the direction in which they're moving. And so thing is, there are two different features. One is where they're moving in a horizontal or vertical, and the other is if they're moving if the color is red or green. So we need to so there'll be neurons that encode for each of these phenomena. I hope you have seen such examples previously. And what will happen is the neurons that encode for red and vertical, neurons that encode for red feature and the vertical feature will have higher synchrony than others. Okay, so this is a temporal binding phenomena that has been observed in behavioral studies, where two different features are synchronously firing to basically give rise to a hierarchical feature representation. So the code for this is not ready, so we will share this, and you can run it independently in your own trans. But so if you have been able to run any of the code files, you can ask me for any questions. And otherwise, also, we are available on the WhatsApp. You can further ask me any questions later on as well. So I hope you have all the four code files. One is a simple mathematical model. Second is the autoencoder. Third is a temporal classification model. And the fourth is differentiation. So with these, in effect, you can actually, if you just change the data set, the cell for data set, you can in effect try to perform any of the tasks, in your own free time, and any of the simple classification task, video prediction task, whatever it is, and you can give, you can see for yourself how well it performs and how does it compare with existing neural network architectures. But for our large scale modeling phenomena, what we do is look at the hidden representations and see how they encode for phenomena that might give insight to how there might be a similar phenomena occurring in neurological in neurons in the brain. So that's the idea. So if there are any questions, you can please ask me.
Sir,
Yeah.
hello. Sir, in any of your experiment, did you consider the volume conduction, or did you eliminate this volume conduction?
We haven't considered actually volume conduction directly. But if you notice, the neural network itself is very artificial, right? It doesn't exactly, reflect the neuronal medium that where the information is actually happening in the brain. So for now, we have only considered information that is flowing directly from one layer to the other. But in reality, information is flowing through various different properties, different mediums, different kinds of neurotransmitters, and so on. So all of that needs to be included in the neuronal model, so that if you're interested in some kind of neurotransmitter idea and how that affects performance, then you will have to include that physically and as the task is being performed. So what we have given is a very it's a bare bones idea, and you can populate it with your own ideas. So for example, in the cortical, specifically in the cortex, there is the idea that nearby connections are strong in the cortex, whereas here we have only considered feed forward directions, right? The oscillators themselves have no connections as in a traditional neural network. So how do we account for that, and how does that affect performance? Those kind of things are still yet need to be studied. And as Sir said, we just published 1 or 2 papers on this.
Okay, thank you.
So volume conduction will require PDEs, partial differential equation, and
Right.
right, and that becomes computationally very expensive. That doesn't mean it won't be advantageous. It'll definitely be very advantageous, specifically if you're trying to study the effect of stimulation, and so on. Effectively, in electrical simulation, there's a volume conduction that takes place that spreads the vector field in a specific direction because of the neuronal medium. And all of those things can be taken into account, but you have to code for it specifically.
Okay. But in naturally, we consider during the phase connectivity, isn't it? Various techniques, that is PLV or
So,
DWPLI.
yeah, even DTI, diffusion tensor imaging, all of this gives rise to some kind of structural connectivity, right? And
Yes.
one of the projects that you'll be doing tomorrow is basically using the diffusion tensor imaging and im- imposing that structural connectivity into the oscillators. That will be done, I think, by Anirban in the next few sessions. But here we are trying to bridge, the neural network type performance to brain activity. And what we have shown are very simple examples that can do that minimally.
Okay, sir. Got it. Thank you, sir.
So, you can please run the codes in your own time, and there are a lot of individual components to each of the code cells. Uh, but effectively, we have seen each and every type. So, for example, you know, I'm assuming the linear ReLU and linear ReLU you have seen in previous workshop sessions. The hop oscillator is the only new addition to the entire neural network strategy that we have studied until now. And that layer is given in this section, in this code file, which is the hop layer. And you can easily see effectively what we are doing is an Euler integration here, and whatever time history you get, that is being propagated further. And you see, and the other thing we noticed is how input is affecting the oscillator's activations, and that is being used by the neural network to classify or to reconstruct signals or to perform integration and differentiation. Okay. And because of how input is affecting the oscillator's activation, we saw this temporal binding phenomena where you saw synchrony among oscillators that encode for the same feature. Okay. So I think that is all done for today. If you have, we will share the code files for temporal binding a little later, maybe by tomorrow. But otherwise, every other, and you can use these neural network files, the neural network classes that we have constructed here for any of the tasks that you wish to perform. Okay. Maybe there's something that is biologically more relevant. So, for example, somebody was mentioning in the lecture sessions the reaching task, right? Where the output should be, maybe the trajectory of the arm moving from one point A to the point B, which is probably performed as behavioral experiments as well. And then you can look at the neuronal activations of the oscillators and how they might encode for information and how that encoding might be similar to what might be there in the maybe in the neurological medium of the person who is performing the task. So this framework allows us to study this. Instead of only being data driven to modeling, we have the model that is able to execute that same task and probably in some way something similar to how the brain might be doing. And let us look at what are similarities, and how we can fine tune the model so that it actually brings out the behavior that we are trying to see. Then this also allows for example, if I were to shut down important oscillators in this neural network, for example, in this autoencoder, if I were to shut down the gray oscillator, then the information is lost. And therefore, that because of which the neural network will not be able to perform. So one of the exercises in the quiz is actually to change the frequency. Here, instead of 1 to 20, you can experiment and put 1 to 5, and you will see how the neural network fails to train. It won't be able to train really well as it is performing now. Okay. So please try to experiment with each of these phenomena and see how performance is and how maybe you can, change this code files for your own experiments. Maybe people who are performing behavioral experiments, and we can also discuss for future. Okay. If there are no further questions, we can maybe stop the session here. All right. Thank you very much. Please take care.